Welcome to my poster presentation. Today I'm going to present you data about error detection in copy typing and which mechanisms are used for error detection and action execution. In motor execution, errors are an undesirable but common phenomenon. Although errors occur quite often, they are not always detected. For example, did you immediately find the two typos in the header? In the present study we investigated how errors are detected. This is a model of motor control and how errors can be detected in action execution. Let's go through the graph together. We start on the upper part, having the intention to make a double click on the computer mouse. With inverse models you may now select the according motor commands which provide information of the selected muscles and the timing of the innervation. Let's go first to the right side of the model. Based on the selected motor commands, your finger will be activated. Depending on your actual position, the arm may be activated as well. You can then see and feel that your finger presses something. This observed information can then be compared with your intention to press the mouse key. In case you pressed somewhere else or that the double click was too slow, you may detect an error and start to select different motor commands. This type of error detection is assumed to be very precise, but rather slow, because the observed effects need to occur first and then the information still needs to be perceptually processed. Let's now go to the left side of the model. Before the motor command is sent to the effectors, it is assumed that an afferents copy of the motor command is used by forward models to predict the action effects. The predicted effects can then be compared with the intended effects. This type of error detection is assumed to be rather fast, because it does not depend on perceptual processes, but only on predictive processes. By this, errors may be detected even before they actually occur. We had several reasons to use a copy typing task to investigate error detection. First, errors occur very frequently in typing. Second, in copy typing the text is standardized, which is not the case for free typing. Third, it is possible to manipulate visibility of distal action effects on the screen and proximal action effects on the keyboard. As you can see on the picture, we covered the screen, the keyboard or both. Fourth, and most importantly, by the number of errors and the typing speed, it is possible to see when an error is detected. Participants came to the lab on 3 separate days. On each day a different text template was used, which was typed in various conditions. The text template was placed to the left of the keyboard, as it would be in a natural copy typing situation. Participants were instructed to stop typing immediately each time that they noticed of an error, to report the error to the experimenter. Then they continued in the template. We made a pre-selection for our participants who were either 10-finger typists or hand and pack typists. Participants who were in between were excluded for this study. 10-finger typists used at least 9 fingers for typing. Hand and pack typists used a maximum of 2 fingers per hand for typing. To investigate reported errors, it is important to know the baseline. In other words, the number of errors that actually occurred. So first of all we looked at the number of committed errors. The number of committed errors did not depend on screen visibility. Further, it did not depend on typing style. One may have expected that 10-finger typists commit fewer errors than hand and pack typists. However, this was not the case. As we will see later in the analysis of inter-keystroke intervals, 10-finger typists typed faster than hand and pack typists. Interestingly, we observed that more errors were committed if the keyboard was covered than if it was visible. What you can see in this figure is the number of reported errors. Because in typing a sequence of letters is pressed very quickly, one after another, participants often pressed some keystrokes after the error until they reported the error. On the x-axis you can see how many keystrokes participants pressed after the error until they reported the error. A 0 indicates that they reported the error without additional keystrokes. A 1 indicates 1 additional keystroke, and the third category consists of 2 or more additional keystrokes. Results showed that more errors were reported with visible screen on the left side than with covered screen on the right side. In our model for error detection, this underpins the importance of the observed effects for error detection. The importance of the screen was even more pronounced in 10-finger typists, shown with black lines, than in hand and pack typists, shown with gray lines. This is not surprising, as 10-finger typists switch mainly between template and screen, whereas hand and pack typists switch between template, screen and keyboard. With covered screen on the right side, most errors were detected immediately after the error. In contrast, with visible screen on the left side, most errors were detected after 2 or more keystrokes. This indicates that error detection with the screen was rather slow. In this graph you can see the inter-keystroke intervals before and after an error occurred. On the left side are the inter-keystroke intervals in conditions with visible screen, and on the right side with covered screen. Unreported errors are shown with a circle and reported errors are shown with a square. In reported errors we did not measure inter-keystroke intervals after errors because reporting interrupted the timing. I will now explain the most important findings of the analysis of variance. As already mentioned before, hand and pack typists in the gray lines typed slower than 10-finger typists in the black lines. What may have caught your eye already is the typical post-error slowing directly after an error occurred. Interestingly, This occurred in unreported errors, indicating some type of error detection that did not pass the threshold of awareness. Further, error slowing was observed in the first inter-keystroke before the erroneous key was pressed. Because at this point in time sensory feedback cannot be evaluated, it may indicate difficulties in action planning or unconscious error detection. Most importantly, in 10-finger typists, the 5 inter-keystroke intervals before an error were slower in reported than in unreported errors. Such pre-error slowing before reported errors was observed in 10-finger typists but not in Hunt and Peck typists. This indicates that 10-finger typists noticed errors before their actual occurrence. Hunt and Peck typists may not detect errors as early as 10-finger typists due to less precise internal models. In conclusion, feedback from distal action effects such as the screen is very important for error detection. However, it is not the only source for error detection. The present data confirms the existence of forward models which can be used to detect errors even before they actually occur. This may, however, only succeed in experts who have more precise forward models than novices of a movement. Thank you very much for your attention. I hope you enjoyed the talk. If you have questions or suggestions, please feel free to contact me via email.